Okay, are you guys ready? Group one here，一拳制人简易。Okay, yeah, please. Okay, start.
Good morning, everyone. Our topic is optimal lightweight design of an I-shaped beam section for small chip layout. Small chip threads are commonly used in factory and repair areas and workstation for lifting and moving parts. However, if the thread arm is over-designed, it increases material cost and also increases the load on the column and rotating base. And on the other hand, if the arm is under-designed, it may cause excessive stress or tip deflection. So the goal of this study is to reduce the arm weight and keeping the stress and deflection within allowed limits. And to make the problem closer to a real engineering case, this study refers to the VHTVB series S-type Jeep frame. And according to the catalog of this frame, the S-type arm is a cantilever beam made of raw profile IPE, and the trolley runs along the IPE beam. So this beam can be regarded as the main load carrying member of the crane arm. And therefore, in this study, we only focus on these horizontal IPE arms and simplify this as fixed three I-shaped beam cantilever. The complete G frame includes many components, and such as the column, rotating support, trolley, hoist, bolt, and wheel. And the crane are in this proposal, we simplify the system and focus only on the crane arm. The column or wall support is treated as a fixed boundary. The lifted load is modeled as an concentrated load, and the beam self-weight is modeled as uniform distributed load. And this simplification allows us to build a clear analytical model for optimization. And next, we define the loading model. For a cantilever beam, when the load is followed from the fixed end, the bending moment and tip deflection become larger, and therefore the trolley and the hoist are assumed to be located at the free end. And this represents the worst case loading efficiency. So based on spherical strip frame design guidance, the design load includes the rate lift load, having 50% of capacity for trolley and hoist weight, and 25% for impact allowance. And so therefore the equivalence end load is defined as the formulation. And after define the load, we define the design variables. The I-shaped beam section is described by four main geometries. It's section height h and flange width ef and flange thickness ef and wedge thickness tw. And this variable directly affect the cross-section area, moment of inertia, and bending stress. And the cross-section area and moment of inertia equation are based on the standard composite area method for I-shaped section. The I-shaped section is divided into two flange and one wave, and the moment of inertia is derived from the standard rectangular moment of inertia formula. And therefore, these equations are used as a geometry basis of optimization model And the bin weight equation is based on the basic mass density volume relationship. Since the material density and bin length are given, the bin mass can be calculated from the cross-section area, and the self-weight of the bin is then modeled as a uniform distributed load along the arc. And the stress equation is based on Euler permeability theory and the standard vector formula. And since the bread arm is simplified as cantilever bin, the maximum bending moment occurs at the fixed depth. On the deflection equation is based on standard cantilever bin deflection formula. And the first term comes from the concentrated angle load, and the second term comes from the uniformly distributed bin self-weight. And because the model is assumed to be linear ballistic, the tube deflection can be added by the superposition principle. And after defining the geometry, load, stress, and deflection equations, we can formulate the optimization problem like this. And this page shows the numerical setting used in this study. The arm length is set to 3 meters because the VHT test type arm length range is about 2 to 7 meters. And the ranging lifting is set to 500 kilograms, which is within the VHT capacity range, and we set a medium small lifting test. And this slide defines the geometry bound of the design prior. Design variable and the bound are selected based on the standard IPE 100 to IPE 300 session rate. And in the other words, the optimization result is not allowed to become an unrealistic IPE shape. And the solver used in this study is sequential quadratic programming, or OSU. And this problem is a nonlinear constraint optimization problem. The design variables are nonlinear and including H, TF, and TF, and TW. And the objective function and constraint are also nonlinear because the moment of inertia, stress, and deflection all depend on nonlinear on the session dimensions. So S2B is suitable for this type of problem because it is designed for continuous nonlinear optimization with constraint. So compared with random search method, S2B is more efficient for these small scale engineering size problems. And the S2B procedure starts from an initializing session, then the program updates the area, moment of inertia, and the bin weight, stress, and the deflection. And also the vector of safety. And if the constraints are not satisfied, S2B will update the session dimension and repeat the calculation until this convergence. And after optimization is obtained, FEA verification is still needed. And this is because analytical bin equations are efficient, but they are based on ideal assumptions. So FEA can help shape the long message stress distribution and maximum tip deflection and possible stress concentration near a fixed edge. And we expect the result is linear optimization IPE arms will have a lower mass than the original design. However, after optimization, the calculating the reliable of optimized design. This is our reference. And thanks for listening.
Of course, this is a problem that you can solve, but I think it's a little simple because for I being geometry, there is already given equations. So if I have those equations, put it in MATLAB income, I can complete this within an hour, right? So I think it's a little simple. So since you are interested in structural optimization, I recommend you to look into something called topology optimization. Topology optimization. In our lab, we have a software called HyperWorks. I think Shanisa is using it. That software has topology optimization. Topology means towards geometry. So topology optimization is a kind of method that will generate very unique design like a art. So you can Google for it. And there are actually some free software on the internet. Uh, I recommend you to try 3D version. Now, if you go Google, there will be a group from I think Denmark. They have free software of topology optimization. They have 2D software and 3D software. I recommend you to focus on 3D. But even you are using their software or HyperWorks to generate optimal design, your effort is still very little. Right? So maybe you can think about having a mechanical design, maybe a more complex system like a robot, multiple arms or something else, with topology optimization structure. Then it's a little complex, but it's not super difficult. Let's say you are building a 6R robot arm, so you have six robot linkages, but not six because for the 4, 5, 6, it's almost like they integrate together. So it's the main big arm here, another arm here, and another smaller arm for the twisting. And usually it's like that. So 1, 2, 3 pieces. And maybe you can treat them separately. Each of them can be designed by a topology optimization. And then you put them together. When you put them together, the torque for each motor will be different, right? So that would be one research work if you are interested in structural optimization. So that's my suggestion. Please go back and think about it. Okay. Okay. Thank you. Next to the group. Next group 2. You guys are not good.
implementation of a version method. And the main challenge here is the trade-off between safety and cost. And while design is strictly regulated by international ASTM, and rigid safety margins often led to structural design. And our goal is to minimize the overall reputation of ensuring 100% compliance with non-linear safety requirements. And to define the problem, we have a design factor X composed of four variables: X1, X2, X3, and X1 is shell thickness, X2 is bed thickness, X3 is inner radius, and X4 is cylinder depth. And X1, X2 is the discrete variable, and X3 and X4 is continuous. And our objective function represents the total manufacturing cost. We've broken it down into three primary factors: the material cost, which depends on the volume of steel; the head manufacturing cost, which involves stamping process; and the welding cost for assembly. So minimizing the function f of x is our primary goal. And this is the table we use. And this table is set up industrial benchmark parameters to connect our theoretical model to computable simulation. And these are fixed parameters from experience studies. And we use C1 to C4 our cost equation. And C1 is a shell material factor. C2 is edge forming factor. C3 is the mid in now well, and C4 is second parent shell well.
To make the problem computable, we adopted the industrial benchmark parameters established by Sensei, and by substituting this coefficient into our model, we write the execution cost shown here. This formula allows our solver to evaluate the exact cost of the optimization of the structural massive, and for any given point of the 4D search space. We also have some design constraints, and these four constraints are non-linear. The first two, G1 and G2, are derived by the ASTM resistant formulas to prevent failure under external and internal pressure and stress. The other two is the first one, the G3, ensures we meet the minimum operational volume requirement. And the last one, G4, is about the maximum allowable length for transport logistics. For the solver, we decide to implement the world optimization, PSO. That's why, because classic methods like Newton or steepest descent fail because we have this problem has continuous and discrete variables. So the particular world optimization fits this optimization problem. And also because PSO doesn't need gradient information. So we can say that this method is robust, efficient, and suited for exploring this complex for this space, search space. We expect to identify the global minimum cost and the optimize design reliably settle exactly on the boundaries of the shell. And so we satisfy the following linear constraints we explained before. And this means we will eliminate all unnecessary material weight while maintaining the exact factor required by the code.
Can you move back to radio formulations? One more. So all of your X are basically geometrical problems. And so from the objective function, it's a very linear problem. And we go next. Next page. So these are like some physical constraints. Um, they are, some of them are nonlinear. Some of them are just linear equations. So please go forward. Yeah. So from here, your statement, the first statement is not appropriate for your slide because you mentioned about gradient-based approach is not good for discrete variables, right? So, but in your problem, there's no discrete problems.
No, the first two are discrete.
Okay, can you show the first two? Not show the first two.
Shell thickness and head thickness are discrete because they follow like commercial size. Like you cannot buy every size you want, so you need to buy like this size, this size, this size, and then the inner radius and the length are continuous.
Yeah. So, but thickness is something that you can solve with continuous.
Yeah,
This problem can easily be a continuous problem. Let's say you are designing for gears, then the tooth, number of tooth definitely is decreased. So usually when people solve this kind of problem, they will just treat everything as continuous, and then when they find the solution, they then choose the closest. Uh, and you, of course, in your optimal design, you for every x1 and x2, you have one design that is slightly thicker, the other one is slightly thinner. So you are not sure if you do the either sealing or flooring, is it going to violate the design, right? So, but once you get the optimal continuous x1 and x2, for both of them, you can try 4 different possibilities. So maybe some of them will be violating the constraint, but some of them will be. So it can be easily solved. Yeah. So with that consideration, this problem becomes quite simple. Um, Maybe you can look into some of the pressure device see if there are more challenging considerations or designs or mechanisms inside a pressure tank or pressure device.
Variable.
I mean, because that is a very standard, has a standard geometry, so nothing surprising. So, but I believe in the market or in reality, there are many more complex designs. Yeah, so if you really like pressure tank designs, then you can go and look into it. Or design for small details, such as stress analysis at some uh, stress concentrating positions. If you design into the details, or in the past, there was a student who are designing like a just a cooling fan. So he is designing something, I forget what, and there are some fans just blowing that whatever geometry. And it became a CFD problem. So whenever he made a change to the design variable, the whole fluid field changed. So he has to run one more simulation for the design. So that requirement to evaluate the numerical analysis is making the problem more complex. It's because more time consuming. If your analysis requires some kind of stress analysis with finite element, then this whole thing becomes very complex. Yeah. So I guess right now everything is being treated as a simple geometry. But if you look into the details, maybe it's not that easy. Yeah, so either you can um, find the gap between this simple design and the reality, or um, find more complex examples. Yeah, I guess those would be two possible ways. Yeah, because it's a project, you don't want to just solve a single problem. Or if you want, I'm not sure if it's useful in this design because there's something called the design uncertainty. So even for manufacturer, when they design for some geometry, they may have uncertain dimensions. So which means every dimension here could be either slightly larger or slightly smaller. Then it's becoming a statistical problem. So if you want to work on that,
Can have random
they
size
when they become random variables, your constraints will become some kind of statistical distribution. So it's like when manufacturers produce this design 10,000 times, certain percentage of the design will have some distribution falling into invisible direction, then which means that percent of the product would be failed product. So usually in reality, people apply safety. So maybe the thickness has to be slightly thicker so it can carry more pressure or something like that. But if you are interested in this statistical approach, I I would like to show this on later weeks. But since if you are interested in this topic, I can maybe arrange an individual meeting and let you know, or send you some papers to show you how this can be becoming a optimization problem with consideration of uncertainty. Yeah, so you decide.
And if we have like a variable that the customer can input, like I know, for the code you need to ask.
That's simple.
So this will okay, so I think
It's just a user input.
I think maybe add random will be the best.
If you consider uh, uncertain design, that's much complex. But it's very complex. It's very complex. So you need to think about it. You may want to search the internet, see if you can find more realistic design to make this not as simple, or move on to what I said, the uncertainty. So let me know your decision.
I think maybe find a complex design.
Yeah, yeah. If you feel like if you cannot find it, then maybe I will show you. So that's okay. Okay, thank you. Next.
Our topic is about optimizing data robot trajectory checking new space nonlinear model prediction. So, data robot is a type of parallel robot. Unlike traditional serial manipulators, the data robot design comes out all driving uniform or analytics and stationary overhead that drives the moving endpoint at the end via a closed dynamic chain by fixing over the epic drive motor to the similar base. The moving part will not need to carry the weight of the motor itself, and this design is significantly reduce the inertia of moving components, guaranteeing the bottom paper achieving high movement speed and acceleration, making making it the ideal choice for high speed and place operations in the history. However, the mechanical structure of this closed dynamic chip is accompanied by strong nonlinear characteristic and high cross coupling between axes. This means that the dynamic response of the machine is not only nonlinear, but the forces acting on the visual motors also mutually constrain and interfere with one another. Currently, the traditional experimental PID controllers widely used in the industry often structure compared to the practically dynamic behavior across the entire workspace when facing demands for micrometer level precisions and milliseconds level response. This is to issues related to accuracy, energy consumption, and system stability when adjust the controller. Upon the introduction of nonlinear model predictive control and effectively handle nonlinear problems, the massive computational burden of traditional NMPC resources serve population delays, and this makes it entirely incapable of meeting the microsecond or millisecond level runtime control requirements of the data robot. Based on the research gap, the objective of the study is to transform the controller into a real-time optimization solver and furthermore, autonomic improvement, we aim to develop a best linear model predictive framework to solve the issue of computation delay and achieve high precision control. First, we address the image scanning modeling of the Delta robot, and the intersection circle model with the geometric function approach is adopted for solving because the end effector of the Delta robot is restrict to pure translational motion. The end of the electric joint CI must satisfy two conditions. First, it must lie on a circular trajectory with the upper arm that big as the radius and the model X AI point as the center. And second, it must lie on a spherical surface with the lower arm effective let let L as the radius and the end connection point at the center. Through the oval geometry contract, the standard trigonometry equation is defined as A sine y plus B cosine y equals to C. And here we see that XP and DE represent the horizontal and vertical relative coordinates of the point with respect to the model X. And AB means a constellation combining the horizontal and vertical system and the upper arm depth. And by simplifying the overall equation, the analytical solution for the model angle like the directly defined. And with this formula, by simply substituting the target coordinates x, y, z to calculate A, and B, and C, the model angle like be obtained using inverse trigonometry functions. And next, a joint space with a body dynamic model must be established. The dynamic model is used to describe the physical relationship between the driving force and the joint position, velocity, and acceleration during the robot's motion. And the joint space with body dynamic motion is expressed as follows. The right side of the equation is gamma, and it means the total torque plus output. And the left side represents the various physical distance force generated during the robot motion. And inframetric term MQ and is a square metric composed of the real number, representing the robot's distance and acceleration and deceleration in its current posture. And I is the moment of the area of the active arm and the motor rotors itself. And P is the next metric of the moving metric. And the Jacobian metric is used to make the end effector next back to the inner shaft in the joint space. And second one is Coriolis and centrifugal metric chart. And it represents the dynamic coupling in interpolating stories generated when the robot moves across uniform axes at high speed. And its metric elements are composed of the joint velocity and critical intervals. And third one is gravity factor terms and the static supporting torque required to overcome gravity to maintain the mechanism's posture. And the impulsion input in this MUMLMD represent the mass of the upper arms, lower arms, and platform, and L represent the total length of the upper arm, the upper arm, and the distance of the center of gravity of the upper arm, and G is the acceleration due to gravity. So the image of this 3D visualization of data robot and dynamics simulations we create using numerical simulation software such as MATLAB, and it is a visualization of the combination of inverse dynamics and dynamic model in the code. And set 100 indicates that this is the moment capture and 100 times that in the simulation, the angle between the current rotation angle of the three models. And to achieve real-time optimal control, we transform the strategy, tra- trajectory, tracking task into multi multi-objective optimization problem subject to checks. And we design a multi-objective cost function encompassing three sub-objectives. And this one is tracking code. The goal of this tool is to optimize the error between the actual position of the end effect and the reference trajectory forcing the controller to maintain extremely high spatial precision. And the second one is stability cost by analyzing the force variation between adjacent time step. This turn prevents the controller from outputting drastically jump commands, and this effectively suppressing high frequency mechanical vibration prone to occur during high speed operation, thereby improving the system dynamics step. And as one is energy cost by handling executing hard large absolute value to force output. This turn prevents the models from consuming exclusive electrical energy during discrete corrections. Achieve the goal of reducing power loss and extend the loss lifespan. And based on the hardware specifications of the two-type delta robots, is that we in, incorporate the following limitation into the NPC logo as constraint to ensure the visibility and safety of the optimization results. And maximum output torsion we limit in between 17 to 20, and maximum joint angular velocity we setting at 10.47, and total inertia we setting at 0.5 to 1.5 times 10 to the power of negative, and the active on angle we limit the range between negative 100, 109 to positive 42, and maximum move space with radius we limit the horizontal movement range of the end effector within 0.6 meter, and vertical stroke limit we limit in 0.35 meter.
calculator to finding the best. And the input is the robot position, robot position test in the inverse technique to get in objective angle and object angle and current angle to Venus and get the error to the Yanni controller to that is just the the feedback forward to the effective function in physics and predict future of series and so use the phase gradient solver to find the phase find the parameters in the future of function. And then some of some of the plugin and the MPC and this is the template and then the output from to the current robot to movement. The executive operator get the current input and current and to run various optical meters to predict the future of function. Then future of the function and then next the end goes to the dynamic model. And then it values that object function in congruent object function to the infinite set and high stable and minimize energy to get the feedback object function and limit change in the angle of limit. Uh, so the cookie is simulated by the complex test the objective function and get the optimal search the direction and convert it out that it will the convergence test it will larger it will larger convergence it will larger error in the executive optimization to do it will uh, uh, it's smaller and yes to check the length and output the parameters and output the parameters to the NNC is the predict the top function and can get the top and then add the PID controller. So it is the set range and get the final output of to the main base control and to the field down and it's fed further with both the checking value like the paper and every time and check and minimize errors in every conditions expect the paper. We hope uh, beside the check error with we hope an optimal output and try therapy and management if this small week there is and method
very good and complete presentation. Uh, so it seems like you already searched for a lot of information and you even show some results. So my recommendation would be just adding a little complexity to the problem. There are some researchers who use Delta robot to do some kind of machining like drilling. Okay, so if you have a drill and a tool tip and you are doing drilling, then there will be reaction forces from the machine that will cause a problem to the robot. So think about some kind of scenario like that to make the system harder to control. So your control, optimal control, a method or optimization maybe can handle that kind of situation. So please think about that. Okay. So for the rest of your presentation, I think it's very complete. Okay. So since it's already complete, you can move on to think about the challenge. Okay. Okay. Thank you. This.
has been expressive or high linear constraints. And all increments will be embedded or implemented. And here's our growth. Basically, we will calculate the initial design and its radius. Then we find the search direction and calculate the distance. And after, update the design and its radius and then if condition is satisfied. If not, then we will repeat the flowchart. So our expected result is achieving 30 or 40% reduction in server water without and simulate explanation result demonstrate the previous that the irregular shape the other is
Okay. Can you go back to your formulations? And constraints. I think you need to define the lower and upper limit of your dimensions. Because if you try to minimize the torque, if the radius and the length is zero, then you have zero torque. So, but that's meaningless. Right? So I guess you may want to have upper bound and lower bound for your variables. Uh, and for your constraints, you have target radius and target contact force. So if you are grasping different object with a different radius, your variable will be different. That means it's a new design. Uh, so it's in reality you cannot do it. You cannot change a mobile hand, right? So I think uh, in mechanical design, in the designing process, if you only solve a problem with one target radius, that's not general enough. So maybe you can define this problem in a different way. For example, you are trying to grasp objects, multiple kinds of objects, different sizes, different weights, different something. And for all scenarios, you have to have successful grasping. So maybe you have a lot of target constraints. It's okay to have a lot of constraints, and maybe many of them will not be active. Only some of them become active. That's fine. Let the optimization handle it. So if you can uh, find more and more scenarios, consider them at the same time, then you will be designing a robot that at least satisfy all grasping conditions. And let's see what's gonna happen. Then maybe it's more interesting. Okay? Yeah. Okay. Thank you. Next time present louder.
industry 4.0, we have the mobile robots and work with them all together in the industry. So we want to find out if we have multiple AMR that work together, how will the potential collection customers happen. So we have the right of the smart logistics, and then we can find out which part will be the automated information can be included nowadays. So while the individual robots are efficient, the multiple robots work together in the we need to find out today. So our goal is to develop an intelligent scheduling and navigation system that can maximize the throughput while ensure zero collisions. So here today we are going to use PSO to find out the best task assignment. And PSO can it will it's like swarm behavior to find out best positions. So we have the rules and we'll have the experience position and the best position. It will find out the best ways to go to the best position. And then we will combination with the A star. And this A star can find out it can find out the best routine in the maze, and then it can find the best maze. So our problem is how can we find out the if we have the two AMRs starting in the industries, and then we need to we have 10 orders, and then be two we will be five tests to each AMR, and then they need to find out the smallest times they need to finish 10 tests. And then the challenge is to the test assignment and then the test planning to work together, and we can find the best competition time. So you will have two decision variables. One is assignment metrics, and we will find it first, and then we will next is the order sequence of AMR, and then we will find the maximize times we need, and it is the length that AMR use and the violence of velocity of the average, and then you will have the burning time. So our solver way is use PSO and then assignment the test assignment, and then you code A star to find out which is the best path to have the best answer. So our result is to have the coverages of plots. We will find out the best answer, and then we will have the past visualizations, and then we can show how our customization have the result.
Okay. Okay. No one's okay. So it's good. But from the first first reference, it's already because the inspiration came from the first paper. PSO and A star are very well developed. I'm trying to think about how we can do something about it instead of just having something that has to accomplish something. Let's see your formation. formulation, the problem. Maybe consider 3D. I'm not sure. Um, if you consider 3D,
Or does have the continuous test applied? Like there's a new test.
because this is already well developed. Just trying to think of something interesting. Not sure. I'm not sure what's the new problem to be solved. Uh, you are you are making it even simpler. It's a grid based. Grid based is even simpler. Right?
Can I suggest something?
Yeah.
Yeah, how about making the two robots different? One can reach higher level, or
They, then it's 3D.
yeah, two
But,
different robots.
but they are simplifying this to a grid base. There's no dimension for height.
How about two robots with different size? One can go smaller, higher, the other one must go.
Then you need to get rid of the grid. So simulating everything in a much accurate.
How about the speed of the robot? One can go faster, the other one can have a speed in.
Oh,
I
because
feel like those are not um, like a critical change. Method wise, it's the same. To think about how the problem can be changed, so you need to do something with the method. So, is there any like a random person in the problem? No person,
uh,
only AMR.
not person, but maybe the
So maybe if you have random person walking around, then it's a little interesting. Maybe you can program the person and allow the person to randomly walk, move, move around, not just like the simply linear moving with a linear speed without making a turn. So like just a very random person. If that's the case, maybe your AMR has to. So maybe your AMR has a certain range of its observation. So AMR doesn't know where the person is only when it's close enough. So when this happens, let's say you are 3 steps away from the person, and if you realize, okay, that position, you need to get away from that position, so you kind of reroute by A star. When you reroute and start to make a move, the random person move again. So you need to keep on rerouting. Uh, maybe when you first see the person and as the person moves within your observation range, there will be like a speed of the movement. You can kind of predict, ah, with all this very limited information, the person is going that way or certain vector with certain speed. So it makes no sense if I reroute toward its future position. You should reroute the other way. It's like you should reroute and then move around its backside, the person's backside, not reroute around its front side because people goes forward. But for math, for for mathematics, if you try to reroute around a cylindrical object, there are two possible solutions, right? If computer doesn't know, if the computer doesn't have some kind of prediction of this movement, then your solution could be one of it. One is reroute left, the other is right. But the one around the person's back is better. So then that makes everything more interesting, but doesn't highly make it too complex. Yeah, so then there will be something, you need some kind of intelligence. And in your optimization strategy, you need to add one or two formulations in there so it ends up with a good solution. Something. Okay? Okay, thank you. Let's move on. Okay, can you show me the design again? So it's a mechanism. Okay. Maybe just 2 slides later. You have so it will be something like this. Right?
Yes.
So you try to design a linkage mechanism that can pass through some desired trajectory. Is that what you're trying to do?
Yes.
Okay. So if you already have some specific trajectory and you found that mechanism which can pass through that desired trajectory, then your design can only pass through that trajectory. Then you don't have some other motions, right? So are you looking for just a simple one-dimensional gripper, which means controlled by one motor, and just one kind of motion for specific missions? Is that what you're looking for? It's okay to have that kind of design object.
I think
So it's really about gripper, gripper design, not robot arm, not robot fingers.
yes.
Because for robot fingers,
Except for one.
just for this is for like one motor control gripper, and you want the gripper to move in a certain way.
But we are looking for only one.
But you know, for robot hand and for the finger, usually it has multiple joints. So it's like you have multiple degree of freedom. Unless it's controlled, it's hooked up by some tendon. So sometimes they have cables or gear chain or tendon. So they still controlled by one motor, but that single motor motion drives all joints and they move together. So that allows single kinds of motion if there is no contact with objects. Um, for your design, do you have like joints? No joints, only finger and then motion. But there's a
There is many joints.
how many joints? Not the mechanism joints, the robot finger joints. 2 joints. So one here, one here. So how many motors? 2 motors? One motor. So because of the linkage design, it's like this one, the motor is at the root. It bends everything. And then because of mechanism, this middle joint also bends. I guess you are doing something like that. Okay.
Our input is the cache.
So do you have a desired trajectory already?
We are doing like quarter arc. So dial
Quarter arc. Quarter arc. How about this? If this is solved, you can use it as example one. And then you can design another desired target. See if the mechanism changes. So you can show multiple target path and just have fun with it and see how the geometry changes. So sometimes you may want to have like a not a arc movement. Maybe you want more like a linear motion or some other kind of motion. And maybe your mechanism can do that. So just get this one done first, and if you still have time, you can try something else. Okay? Great. Let's continue. minutes.
Other read about robot testing documentation. And this is and the research that is because nowadays the robot test planning is quite applied to autonomous driving robot and driving and logistics system. And the traditional algorithm can find the physical test, but it's not it's the linear distribution. And so this study is a combine of this line and PSO to generate the smooth and collision-free test by acceleration control points, aim to improve testing quantity while maintaining the communication efficiency. And the source is the PSO, and PSO is a well-inspired algorithm, and it's based on social behavior of growth marketing and peaceful. And the smart intelligence is individual shared person experience and the global experience, and to find the optimal solutions. And this is our functions. The function is J and is equals to W1 times L and W2 times C. And L means the path and the C means the number of conditions. And we want to minimize the J to find the best solution of this J, the path. So we set some constraint like P1 to Pn, and the collision is T, and D is uh, the robot test and the optical length. And still the boundaries is xi and xy is equal x mini, x max, and y mini y. And this is PSO's um, formula. We can see omega is inertial weight, and C1, C2 is the acceleration coefficient, and R1, R2 is the random number. And we will use this B to update the position of our point. We can see the xi is equal to xi plus vi of t times t plus 1. And this is our workflow. And initially, we will write down some points and velocities. And next, we will evaluation of j. And next, we'll update p and g. And move to a new position and change the velocity. Next, if it converts or it to the limit, we will exit and output the result. And this is the test environment, and it's like some complicated map puzzle or some not a good thing to move. And our exact result is to combine B-spline and PSO to find the global optimal and minimize the J. And we will balance the path and smoothness and the abnormal noise and do not collect anything. And to ensure the robot will not collision, we will beat the merging D set. And we will improve particular search division to achieve faster conversion and fewer iteration. This is our reference.
Okay. Can you go to one of your simulation slide? Yeah. So you are moving on pixels,
Uh,
right?
yeah, it was Yeah, it's the setting.
So it's going to be your grid is a pixel.
Grid.
The grid on the
Top, yeah.
yeah. You are moving on pixel accuracy.
I think this is to set the environment. Yeah, so
Okay, so yeah, you are moving on the pixel.
yeah.
Okay, so trying to think about how you can make this problem more interesting. Yes, so these
Maybe it can be a 3D because each line can move the cat.
for your case, if it's 3D, it's more like a UAV flying robot.
Oh yeah.
Uh, I know there is a problem. I'm not sure if your team can handle it. There is a kind of a problem called a collaboration between multi-robots, especially for moving one object together. So let's say two people is moving a box, moving a big box, and one people holds this side, the other people holds that side. So like moving a sofa. When they're moving, they need to synchronize their movement. And sometimes around the corner, they need to like parking a car. They need to figure out how to move. Oh, okay, so it doesn't collide. Uh, for that kind of problem, you need to calculate the synchronized motion for both robots. So that would be something interesting. Synchronized. But actually, because it's not a control problem. So in your calculation, there's no delay.
Yes.
You can easily solve for the motion of the first robot, and the second robot would be somewhere around the first one with some kind of radius. So their distance are kept the same all the time. And also you need to consider some geometry. So when you are working on collision avoidance, you actually handle collision between the object and the wall, right? It's because for pixels, they only overlap then they collide.
Yeah.
So for your problem, they
Also,
it's not easy for them to collide unless you
yes, but we deny the collision, the D set, and maybe it will not only just zero.
yeah. So it's like a safe margin.
Yeah.
Safe margin is like offsetting everything.
Yeah. Yeah.
Offset the wall, offset the center to a greater size. Then it's the same problem,
Okay.
right? Yeah. So if you have geometry that can during the movement, it could be moving around in a random position. It's more interesting. But if you look at your senior genes, physics, basically that's the problem.
Yeah.
So please think about what you want to do, because this is already very well developed field. See what's challenging, and you can give it a try. Okay? Okay, thank you. Next.
about optimal design of heat sink for electronic cooling. Electronic components generate heat during operation. If this heat is not removed efficiently, the component temperature increases, reducing performance and reliability. The goal is to design a compact and lightweight heat sink that keeps the component temperature within a safe range. So the objective is to optimize the heat sink geometry in order to meet T base and also it mass load, where T base is the temperature at the base of the heat sink where it contacts the electronic component. These variables are the number of fins and H is defined the fin height, sorry. T is the fin thickness and S is the spacing between fins. The design must satisfy practical limits like the length, the width, and the mass must not exceed the allowed size for the case of the length and the width, and for the mass, the allowed weight. The base temperature must stay below the safe operating temperature, and thin spacing must not be too small because airflow will become restricted. So this is a simplified physics-based thermal simulation that T base is equal to the ambient temperature plus the heat generated times the thermal resistance of the heat sink. So these are the formulas, the resistance formula, the efficiency formula, and M for to find the efficiency. This makes the simulation more realistic because the entire thing is not assumed to have the same temperature. So the objective function is this one. J is equal to W times the allowed temperature plus W2 times the allowed mass. W1 controls the importance of cooling performance and W2 controls the importance of reducing mass. This means the algorithm search for a design with low temperature and acceptable mass. A genetic algorithm is used to optimize the heatsink geometry because the problem has several variables, constraints, and possible non-linear behavior. The genetic algorithm works by creating many possible heatsink designs, evaluating each design using the objective function, selecting the best designs, combining and mutating them to create better solutions, and repeating until the best design is found. So, as you can see, for this test, I select numbers of fins n is equal to 10, the height h is 30, the thickness is 2, the thin spacing s is equal to 3.3, and parameters like m and the thin efficiency and all of that around here. The assumptions like Q, the heat generated by component is 30 watts, ambient temperature is 25 degrees Celsius, and this is practically a summary of the initial design and optimized design that I will show later. And these are the improvements. With a temperature reduction of 26 degrees Celsius, a temperature reduction of 35%, and more properties that I will talk about with this graph. So the result temperature, this represents a reduction in base temperature after optimization of 26 degrees Celsius or 36%. The result in mass, as you can see, the mass increased from 140 to 137, but remain below the maximum allowed mass. This happens because we add more fins from 10 to 17 and reduce the space between them, and we increase in the height. For that reason, we have this increase from mass of approximately 20 grams. These graphs show the convergence of the genetic algorithm J. As you can see, the genetic function decreased quickly during the first generation, meaning that the algorithm finds better hits in designs. After around 8 or to 10 generations, the curve becomes almost constant, as you can see, like a straight line here, which indicates that the algorithm has converged to an optimized design. Now the trade-off about the temperature versus mass feasible designs. As you can see, this is the initial design here, and this is the optimized. As you can see, it's the with the less temperature possible, but with a increase of mass here. This graph shows the relationship between heat-sink mass and base temperature for different simulated designs. Each blue point represents a possible geometry evaluated by the thermal model. The initial design has a lower mass but a higher base temperature, and the optimized design increased the mass slightly, but it significantly reduced the base temperature, as you can see here. This shows the design trade-off between cooling performance and weight within the allowed. allowed. And for the final comparison table, here, as you can see, the initial design was 10 fins of the height of 30 millimeters and a thickness of 2 millimeters with temperature base of 22.43 degrees Celsius with this mass and this result jet. As you can see, there's an improvement of the temperature base temperature, sorry, and of the jet. So, in conclusion, this project is a simulation-based optimization approach to improve heat-sink geometry, and the genetic algorithm reduced base temperature while satisfying size, spacing, and mass concerns. So,
Okay. So you have done the project. You finished the project. Have you finished the project already?
yeah, and I try with just one sample.
But today is just proposal. Really?
Yes, I didn't know. Also, I finished.
Okay. Explain to
Sorry for
me
Okay.
what's your chromosome design.
The design
Chromosome.
from
You use GA, right?
Yeah.
So what's your chromosome design? Okay. So did you use MATLAB?
MATLAB. Yeah.
Then
the-
you don't know the
I don't-
detail inside.
No, it's just
Okay, then you have something to work.
okay.
Why do you use GA? Do you know why do you use GA?
No. Okay.
Why do you use GA, genetic algorithm? GA?
I know. I just used that because it was the most simple that I found.
Say again? I don't
It was
understand.
the easier method that I found because I'm right now with heat transfer and all of that.
Okay.
So this is related to what I studied,
Okay.
like things.
So it's just a random choice
Yeah, just
from
random
Google,
choice. Yeah.
from
Yeah.
internet.
Yeah. I just found this option and I said, okay, I'm sorry, right now. Heat transfer.
So
So I selected.
this course is about optimization. So
Yeah.
you need to justify why you choose some method, and then everything needs a reason. Okay, so I can tell you why. If you move on to your design report, here, the number of bits is this. So if you use some other methods, well, was introduced in the class, they are continuous methods. GA is good for discrete variables, so it's a good choice. Okay, and but I want you to know how you design the product, and it's related to something called chromosome. So I will, since this is the beginning of the project, So I want you to go back and figure out the details. And can you go to the updated function? Okay, so you have two weighting coefficients. So this kind of problem is called multi-objective optimization. Okay, so I saw your results show a bunch of plots, a bunch of points. Are they design points with different selection of weights?
Yeah.
Okay,
Yeah. Also because
so you sample different weights.
yeah, different weights and different weights, different okay, all for
Okay, so in multi-objective optimization, there is something called Pareto front. So the frontier of all these points on the very left and bottom edge is called the Pareto front, which means all the points on this frontier, they are all optimal solutions. They are solutions representing different weights. So the green point is the optimal design with the lowest temperature. And if you move that point to the very top on the left upper corner, that is the design with a minimal mass. So I guess two different things are trading off. If one day a designer say, okay, let's do 50-50, then the design point will be somewhere in the middle. So this curve is called the frontier, and it has a name, Pareto front. Pareto front. And in multi-objective optimization, this front is a collection of all the possible solutions. When that happens, usually there is a difficulty of choosing optimal because they're all optimal.
okay.
They're all
It's
optimal.
a straight line, but in this case it's
This,
not
this curve, they are all optimal solutions. Here. All the points right here, they're all optimal solutions. They are a collection of solutions with different choices of weighting coefficients. Okay? So since you bring up this kind of problem, I want you to know that's the solution.
so you have to talk about the like
Yeah, I mean, later on you should present it that way. You should let us know. Okay, that's a Pareto front, and there are multiple solutions here. And maybe you can show how the design evolves from one side to the next. Maybe the one at the bottom has lower number of fins, so it's no, the one at the top,
Yeah.
lower number of fins, so it's less weight,
last way.
but
Like
But it's
35 or
hot.
something.
but it's hotter,
Yeah.
something like that. So since there are still several weeks, I will suggest you to study something and then see if you can make this problem more interesting. Okay? Thank you. Next.
That was the last one.
You're the last one?
Okay.
Oh, you're the last one. Okay. Okay, great. Okay. So I gave you some suggestions. So those are just suggestions. You can consider them, or you can think of something different. The purpose of those suggestions are just giving you some kind of challenge. Because I know when you look for some projects, there are a lot of references that's useful for you, and most of the time, those references are already complete results of some complete research. So nowadays with AI, it's easy. You can easily collect known information together and get a report done. I know. So that's why I give you. I want you to give yourself a little challenge. Think of something that may not be considered yet in the literature, or only a few people consider it. So if you challenge yourself, then you need to think about how you should modify your formulation, how should you correct your solver, so you can see different solutions. Okay, so I think that would be an important practice because later on in your, if you're working on a master thesis or senior project, or in the future you are just writing something for a research report, uh, you always want to show what's novel, what's new in the research, right? And this is a good practice for this course. Okay, so later on at the end of the semester, if you can show something pretty interesting, I will recommend you to. I will forward your work or recommend your work for uh, some conference publications. So if you are interested in conference publications, uh, you can spend more time on this final project. So if I think, okay, this work is very interesting and we should publish this work in one of the conference in Taiwan, I will, my research team, my budget will pay for your registration and travel payment for the conference. So you can go there for free. And but of course, if for example two members, one is my student, the other one, for example, is some other professor's student, and if this paper, I think that you guys did a good job, we publish it in the authorship. You two, of course, will be in the authorship, and your advisor, the other advisor, and myself, we four can be the authorship together. But I need to send an email to confirm with your advisor, see if he or she agrees. Most of the time, they will agree because that doesn't. I think I won't be asking for help from your advisor. So just I want to give you guys some opportunity to have a conference paper during your academic years. Okay. So including the undergrads, if you are working on something and really interesting results, I can recommend that for conferences. However, if you are like short visiting students, most of the Taiwanese conferences are in the second half of the year. So it's usually after September or October. So I'm not sure if you guys are still here. So anyway, but if you end up with some interesting results and with a conference paper, I guess it's also good for your career. So anyway, so please work on it, and if you have questions, feel free to let me know. Okay. I think next week we have exam, right? So let me remind you how I will give you the exam. So it's about linear programming and also KKT condition, right? So I will give you a problem such it's definitely a 2D problem. So it's gonna be minimizing some kind of uh, make it more clear. Minimizing C1x1 plus C2x2 subject to several constraints, and they are inequality constraints. So it's gonna be some kind of, for example, A1x1 plus A2x2 smaller than B1, something like that. Da, 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 many of them. So all the x will be positive. So basically, in the design space, it will be some kind of closed boundary with multiple constraints, which are these. These are the constraints. And also, x1 and x2 must be positive, right? So these forms this a closed region. And the contour, for example, contour of the object function is going this way, then we usually start from the center. So it could be moving here, and maybe going here. So that would be the optimum, something like that. But how do we move from the origin? We need to introduce slack variables. So remember, go back and figure out how to introduce slack variables. So the inequality will become equality. So you will introduce more variables and solve by hand. Okay? Once you're solved, during the optimization process, I will ask you to use KKT to check the solution for every iteration. So every iteration. Okay, so let me remind you, after one iteration, you need to find out, okay, this is the design point after one iteration. I want you to use KKT to check if this is optimal. Supposedly, it won't be. Then, another iteration, you found the solution here. You need to use KKT to check again. Supposedly, it won't be optimal yet. And then, if you move some to here, and then you use KKT to check, okay, yes, it's optimal. So, you are supposed to be able to perform linear programming and perform KKT. And I can tell you, if you know how to do it, this exam you should be able to get 100 points. Because LP is a kind of problem that you either know how to do it or you don't. Right? So if you know how to do it, you shouldn't be able. I don't think how you can make a mistake. It's just a certain process you need to repeat and repeat again. Right? But if you don't know how to do it, probably your whole solution sheet is gonna be blank, and you just hand in and you got 0 points. So please, this time, practice how to do it. At home, formulate some kind of problem by yourself. Perform one LP, check by KKT, LP, KKT, LP, KKT. See if you can do it by hand. And see if every solution process is making sense. Okay? During the week, if you see any issues, you can send me emails. Okay, you can write down the whole thing and then show me. I can maybe point out where the problem is. Or you do your hand calculation, send to GPT, tell XGPT, and tell me why. Tell me where I make a mistake. But if you ask GPT to solve it for you, GPT may not recommend the same method because there are multiple ways to solve LP. The way I'm introducing may not be the exact one GPT is recommending. Okay? So please use the method I teach. Any questions? So you may want to give GPT my notes and my meta code and tell GPT, okay, my teacher taught this. Later on, when I can solve a problem, please use what my teacher taught me to check my solution process. That's one way to use it. Okay. Okay. Next week I won't be here. I will be traveling to USA for a conference. So TA will be here and deliver the exam sheet. So I think the exam should be very easy to understand. It's something like this, just one big problem, but it takes time to solve. Okay? So I guess I won't be here to, I don't need to be here to explain the problem. Okay? See you, good luck to the exam. See you 2 weeks later. Okay? About the makeup for exam 1, I think we can do it after I come back. Okay? No rush on the makeup of exam 1. Okay? Thank you. Bye-bye.